So we're gonna talk about, so solids are just basically 3D shapes. And they want us to find the value of x here, and this is, again, SOHCAHTOA. We will be using that this chapter, so not going completely away from that. So in terms of our SOHCAHTOA, we have adjacent and hypotenuse. So we're going to use cosine. Adjacent over hypotenuse is 5 over x. So this is our tougher one that we have to do. So in order to solve this, I like making it into a proportion. So I put it over 1 and then cross multiply. And then in order to solve that, I'm going to divide by the cosine of 70. And I'm looking for that that hypotenuse, so I know it's going to be longer than 5. So just making sure that my answer turns out the way I'm kind of anticipating. I got like 14.6 for my x value, and that seems to make sense based off the drawing that I see. So getting in lots of vocabulary words today, lots of just talking about what different shapes like are, what they look like. I probably, again, since I don't even know, I actually made this note packet just before break, but I realize now I have other note packets, so I probably put too much in this one, but that's okay. Probably doesn't hurt to talk about them. All right, so a polyhedron is basically a 3-dimensional shape. So, the more technical definition is it's a solid that's bounded by polygons. So that means each of the sides of the shape is a polygon. So if you notice on the bottom down here, I have examples of polyhedra, that's a single, polyhedron is plural, versus not polyhedra. And the reason why these ones on the right are not polyhedra is because one of the sides is a circle. Or like the sphere doesn't have really any sides, it's just, so basically, the ones we're talking about today are called polyhedra, so a solid bounded by polygons. Now the other ones are shapes we're going to talk about this chapter, but they're specifically talking about polyhedra right here. And those polygons are called the faces. So those are basically the outside part of it. So and I mean, there's all sorts of polyhedra, like all over the place in this room. Like I have a Kleenex box, the polyhedra. You know, we could talk about like this little pencil cup is a polyhedra, because all the sides are polygons. Now, the edge is where two sides or two faces come together. So it's the line This would be an edge. I realize I should be labeling on here. So the green thing would be an edge there. This would be a face. And I always think of the edge being like, if I was gonna like glue a shape together, where would I put the glue? And I'd put it like right along the edge of that. Our next term is the vertex, and that's where the the edges come together. So like the corners on a shape, you maybe would call it, or the points. So on the corner of my Kleenex box, that would be a vertex. So we have faces, we have edges, we have vertices. And we're going to talk about all these, but again, polyhedra is the one that has to be formed by polygons. All right. All right, so our next terms so a prism, and we'll talk more about a prism tomorrow, but it's formed so a prism is formed by two parallel faces. So like, for instance, our Kleenex box would be a prism because the top and bottom would be parallel sides to it, so that'd be a prism. Oh, and sorry, two parallel should be congruent faces. So I'm actually going to point it out down here. So this is not a prism down here. So it's formed by two parallel congruent faces. So the one down on the bottom is not a prism because of the fact that the bottom and the top are not the same size there. Whereas this one over here is a prism. This is also not a prism. Okay. Our next one is a pyramid, and it's exactly what it sounds like. It's basically the base is a polygon. And then a pyramid, just basically all the points come up together at the top. So they connect the faces. So like down here, this would be an example of a pyramid. So we're going to name these, and in order to name them, we have to name them using their base. So we name using the shape of the base. So I'll show you guys down here. So since the first one's not a prism and it's not a pyramid, I can't name it this way. So this would just be a polyhedra. Whereas the second one there is a pyramid, but we look at the bottom of it, and I look, and this is a six-sided shape on the bottom, which is a hexagon. And I won't make you name these, so we call this a hexagonal pyramid. So its name is based off the shape on the bottom. So it'd be a hexagonal pyramid. This next one is also a prism, but the bottom is a rectangle. So it's a rectangular prism. So again, being able to name them for a test is not necessary, but just being comfortable with that. Now it asks us to also find the number of faces, vertices, and should be edges, comma, edges. So trying to picture, we don't have to do all of these, but we'll kind of see how we do here. So, in terms of the faces of this first one, I only see 3 of them. But remember, there should be one on the top and the bottom. That'd be 1 and 2. There's these 2, and then there's 2 on the back side. So this would be 6 faces. So top, bottom, these 2 we see, and then there's 2 on the back side. Vertices, again, we have to count even the ones we can't see. There's 4 on top, there should be 4 on the bottom. So there should be 8 vertices. And then edges, those might be I don't know, tougher to count, I'm not sure. 1, 2, 3, 4. There's gonna be the same on the bottom, so that'd be 8. But then there's also 4 across the sides, so there'd be 12 edges. So the same thing with this next one here. So again, faces. If there's 6 sides, there's 6 faces, but then there's the bottom, so there's 7 faces. Vertices, there's the 1 on the top, and there's 6 on the bottom, so 7 vertices. And then edges. There's 6 on the sides down here, and then there's 6 of each of the edges that go up to the top. So 12 edges. We'll skip the last one for now, just because it's the same as the first one we did. All right, so let's talk about something being a polyhedra. So this isn't asking it about being like a prism. So any type of shape that is bounded by polygons. So this is a polyhedra. Whereas this one has this curve, so it would not be a polyhedra. Because of this curve. Now, as we talk about these faces, vertices, and edges, I'm going to show you guys this, what they call Euler's theorem. So Euler's a guy who's super, super old, so anytime you get mad about math, is probably one of his rules that we're coming up with. This one they actually named after him. And there's a formula that if a shape, so this works for all polyhedra. So F plus V should equal E plus 2. And hopefully you realize that F is faces, vertices, edges. So it's kind of a good way to check. So anytime I'm kind of doubting myself, I'll use this formula to help me. So our first one here with our polyhedra, again, our faces would be, there's 1 on the bottom and 4 around the side, so there'd be 5. Our vertices would be 4 on the bottom and then 1 on top, so 5. Our edges, there'd be 8 of them, because there's 4 across the bottom and then 4 on each side. And so if I do this, if I add these two together and then I add 2 to this, they should be equal. And I feel like that sounds like a totally made up rule that he's like, oh no, we just have to add 2 to the edges, but it works every time. So it's kind of crazy that way. So again, here, we can't do it for not polyhedra. So our face is on this one, so there's 2 on the front and the back. There's 1 on the bottom. So I think 5 faces here. Our vertices, there's 3 on the front and 3 on the back. So 6. I believe we had 9 edges. And again, plus 2, they should equal each other. And if you looked up Euler, he's probably one of those guys who wore the weird wig, like with white hair, like he's kind of a old dude. So he came up with this rule a long, long time ago. All right. So I would say if you got something out of this, being able to use this rule, again, the name's probably not quite as important, probably not going to worry you about that as much. All right, so when you guys are flipped over, it says, oh, I guess we just did a pyramid, so we probably don't need to do example 3. All right, so our next one we're going to skip to is a regular polyhedra. So a regular polyhedra is all faces are regular polygons. And if you guys recall, regular means all equal sides and angles. So my Kleenex box is not a regular polyhedra. Like a perfect cube would be a regular polyhedra, which I don't know that I have. But like our Kleenex box, the sides aren't all equal. The angles are all the same, but the sides aren't all equal. So this would not be a regular polyhedra, still a polyhedra, but it would have to be like a perfect little cube. Like a Rubik's Cube would be a great example of a regular polyhedra. So the shape we have here is a convex polyhedra, but it's also a regular one because it has all equal sides here. It's an equilateral triangle on all the edges. But then they have a concave polyhedra. This one's not regular. But if you guys notice, it's kind of going in the shape. So like it's kind of dented in, but it's still a polyhedra because all those sides are polygons. So concave, it can kind of break in there. And I just drew some pictures of some great examples of regular polyhedra. Again, these are all regular. When I was in 7th grade, my class, we got to make big paper versions of these. We got to hang them from the ceiling. And I tried looking for that as a project, and I realized my teacher spent a lot of time trying to make the little shapes work out perfectly so that we could build these. So I did not choose to do that, and it would be really expensive on the paper I need, but, because you need like thicker paper, like cardstock. So, but it was pretty, I mean, it was a pretty cool project, but we did all these different shapes like those. So, next thing we're talking about is a cross section. So if you can picture taking a shape like these, and we're gonna basically slice part of it off. So a cross section is basically cutting part of our polyhedra off, or our pyramid, or whatever it has to be. So it's a plane that intersects our shape. And part of it is that cross section is going to form another shape. So like what they have highlighted there, I know yours isn't in color, but we have highlighted there kind of in like a fuchsia or like a purplish color, is the overlapping, like what does the cross section look like? So if I sliced it, what would my like the bottom of my slice look like? So this one, the cross section is a triangle. And depending how they slice it, it might be different. So that's what we're going to get into, and then we'll finish up with just some finding missing values of n. So lots of writing today, I apologize, lots of vocabulary. Tomorrow we're going to get some new formulas for these different shapes and how to find we're talking about the surface area of them. So they want to know about the cross section here. So if you look at this cube here, and the cross section is like the little pink part, I'm slicing that off. What's the shape of that cross section? Can you tell? So if I took, what's that? I don't think so. So if I took and I sliced like the corner of, like, picture this as a block of cheese, and I sliced that through, like a straight slice here, what shape would be left, like, kind of open? Yep.
Triangle.
Yeah, it's a triangle. And so it's like a like it kind of is in 3 dimensions. So trying to picture that little pink part would be a triangle. So we're not looking at, and I think maybe you're looking at the whole thing, we're just looking at the part that'd be like left exposed. We have a cone here that's sliced. What would be left of our cone? It's that cross section there. It's just a circle, yep. And then our last one, kind of a different one here. Again, they're slicing our cube, but they're slicing it further down. Can you tell what that pink part left is open? It's like a trapezoid, it looks like, because it's not exactly like a rectangle. The bottom is smaller than the top. So it kind of looks like this to me, is what it pictures, like what I'm picturing. Okay. The last questions they're asking us to do is find the missing value. So they basically are using this formula that we learned, the faces formula, the faces and sides, that we said f plus v equals e plus 2. So this just becomes an easy algebra problem where they're not giving us all the information. So our faces, they tell us that's 5, plus our vertices is n, our edges is 8. So just a simple algebra problem. If I know the other parts of it, or if you're having trouble determining how many, whatever it happens to be, so there'd be 5 vertices here. So hopefully some pretty easy algebra. So a more complex face there with 20 faces. All right, questions there at all? All right, so thanks for hanging